share and maximize these slides. Nice. Okay.
Good.
Okay, cool. So I'll get started. So first of all, of course, a big thank you to the organizers for giving me the chance to speak. It's a real honor to be speaking amongst all of you at this conference. So for those I haven't met yet, my name's Ed. I'm currently finishing my PhD at City University. And despite usually being based in London, ironically, I'm tuning in from deep in the Canadian Rockies. So despite the unusual setup, I do have a snowy scene behind me that is quite pretty. So today I'm going to be talking about a project I worked on, or we've just finished with my supervisor, Professor Yang Hui, who spoke earlier today, and of course one of the co-organizers here, Professor David Berman too. And it's been really good fun. The title is this machine learning Calabi threefold hypersurfaces in weighted P4. So we're going back to look at this classic databases of weighted P4s from the 90s and using some tools of supervised and unsupervised machine learning to analyze them. And I put an archive number down here. Excitingly, we actually managed to post over the weekend, so I've got my fingers crossed there'll be no hiccups and it'll be coming out as an early Christmas present in the next couple of days. So to go on to talk about the overview of what I'll be talking about today. So first of all, I'll just sort of reintroduce that data set, talk about how it's structured, because it's been a while since it's been looked at thoroughly. And then I will go on to talk about some generated data sets we also create, which have similar properties, but we use these as sort of benchmarks for analyzing performance of the machine learning techniques. And then also sort of to compare and these analysis methods too. So from there, we'll go on to talk about some unsupervised techniques. So we sort of use the prototypical linear PCA, and then we do some clustering as well based on Hodge numbers, and we get some interesting behavior based on that. And then from there, I'll go on to talk about the supervised methods that we used. So learning these topological parameters and learning this Calabi-ness from these weighted projective spaces. So as I said, first of all, just to review the data. So this data set we took from the Hirst database online. Obviously, everything's set up there to be so easy to download and work with. So big thanks to them for that. And this database was set up in the 90s. Obviously, there were a large number of people did excellent work to construct this. Candelas and Hirst, Batirev, too many to list. But the data set specifically is these 7,555 5 vectors of weights, and each of these defines some weighted P4 space. And these are the specific combinations of weights that create weighted P4 spaces that admit Calabi threefold hypersurfaces within them. So in a sense, a very special database that permits these hypersurfaces to be constructed within them. So in each case, we have, so I'll give an example of what the database looks like. We have this 5 vector of weights, and on top of that, we also have a 2 vector. These are the 2 non-trivial Hodge numbers of the threefold hypersurfaces within them. So yeah, a very nice database to be working with. So I should add that these 5 vectors are sorted, so the largest weights are at the end. So when we do a sort of initial frequency distribution analysis, just to sort of get an idea, a sense of the data set, we sort of see how the weights 1 to 5 are sorted, and we have a higher density for lower weights lower down. But in general, just from this plot, you can see that the distributions of the integer values they take tends to, or by eye, appears to follow some exponential style distribution. So we specifically fit an exponential to this and use this fitted exponential as the probability distribution for creating our generated data sets. So these generated data sets, again, I mentioned briefly earlier, we use these as our benchmarks to compare our performance to and compare our analysis with. And we generate 3 specifically. The first I call random, the second co-prime, and the third transverse. And these are just these are supposed to be sort of levels of the data. In each case, we're introducing another condition that's required for the space to admit a Calabi hypersurface. So we sort of have a layered levels of data, with each one becoming more specific and closer to the Calabi database. So just to reiterate this random database, this is just a random 5 vector of integers, positive integers, and specifically these are constructed so there's no overlap. This isn't a filtration. There's no coprimality. And then in the second case, we have a 5 vector of coprime positive integers, and these are constructed so they're specifically not transverse. And then these transverse, these are again coprime positive integers, but now they satisfy this transversity condition. And it's sort of divisibility condition based between the weights, such that each weight will divide some linear combination of the other weights. And specifically, transversity is a necessary but not sufficient condition for the weight of P4 to admit this Calabi hypersurface. So it's again, it's like a stepping stone in our adding conditions to the data sets. So overall, that gives us 4 databases that we're working with. This Calabi database being at the top and the most interesting one for us to look at. So after we've constructed these, we wanted to do some analysis. We used some unsupervised techniques, and specifically, we first off start with the sort of the most prototypical machine learning unsupervised technique of linear PCA. So just to very quickly review for those who may be less familiar, PCA, we take the covariance matrix of the data. So for this database of 5 vectors of weights, we see how they vary with respect to one another. And because we have 5 vectors, this produces a 5 by 5 symmetric covariance matrix, which we can then do analysis of. And the PCA method diagonalizes this such that the eigenvectors are then principal components. And then we sort these principal components according to the eigenvalues, the variance sizes, such that the first principal component is the direction, the linear combination of the weights, which has the largest variance, such that this sort of represents the core structure of the data. And then, again, successively down through the weights. So we perform this PCA independently on each of these 4 databases we're using throughout. And as you can see, the first 2, the random and co-prime, they look very similar, as you'd probably expect if linear PCA could pick out co-primality. Maybe the Riemann hypothesis might not be as difficult. We'd have some big jumps in prime analysis, but obviously that's much more complicated. So these look very similar, but we can see some sort of cone-like structure in the data. This is throughout all of them, and this is based on the weight sorting, or we conjecture to be. As one might naively expect, as the weights are sorted, the largest weight is at the end. So the largest variance you might think would be associated to the last weight. And there is some sort of correlated behavior to this, but it's not exact. So, the largest contribution to the largest principal component comes from the largest weight, but it's not exclusively that weight. So there is some more subtle structure. But this is just what I'm trying to say here, is that as the largest weight roughly increases, the sort of second largest principal component, the range it can take increases as well, as there's maybe a rough correlation to the weight ordering. So as I said, beyond the cone-like structure, these first 2 databases, there isn't much structure to see here. When we introduce this transversity condition, there is some more structure starting to occur. Maybe there's a sort of separation into the 2 forks perhaps, but it's quite hard to see from this database. But most interestingly and excitingly, when we look at the Calabi database, we have a really clear separation. Definitely by eye, you can see there's a separation into classes, particularly with sort of certainly thicker classes at certain points, as we have this linear relationship between these components for different values of different weights in the database, different weight sets. So I should also say that throughout this, we've used linear PCA, the simplest form of PCA. And we did try other kernels for different kernel PCAs, but interestingly enough, trying a variety of polynomials and Gaussian and sigmoids, linear kernels actually gave us this sort of most interesting behavior, this clustering style of behavior. And where this comes from, we're going to conjecture is related to Hodge numbers, and that's what I'll move on to here. So as I said at the beginning, the database came with these 5 vectors as well as the 2 Hodge numbers. So we can just do some simple plotting amongst these parameters. And the most interesting result we got from this was plotting the largest weight against the first Hodge number, H11. And again, we sort of see a similar relation. We're then getting this an unexpected linear relationship between H11 and the 5th weight once it's been split into classes, where we sort of have a familiar clustering behavior, which we say looks alike this PCA kind of structure, since we have weights correlated to principal components. So this seems like a very nice problem to do some clustering analysis on. So we first of all reduce this to a one-dimensional problem. Since we have these what appear to be linear lines, we just reduce everything to its, I guess, gradient through the origin, but it's really just the y over x value, the H11 over the 5th weight. And then looking at the outer data where there's more prominent structure, we can see from this histogram that we have clear peaks in the data. So again, just reinforcing this is a good problem to do some clustering analysis on. So then doing the clustering analysis, we use specifically k-means clustering as the method. Here we use some sort of adjusted normalized elbow method to determine the number of clusters to use. It came out as being 10. And here we have a plot of the bounds of the clusters. As you can see, for the outer, the data further from the origin, we see some sort of a nice separation where it splits up and really does bound these lines as we would expect. So sort of reinforces this clustering structure we're seeing by eye. And to give some quantitative encouragement to this as well, we use a sort of normalized inertia as a measure. So this you can see is a very low value, close to 0. And then we can sort of interpret this as being that each data point or each ratio data point is roughly or is less than 0.1% the total range of ratio values from its nearest cluster. So this is already, again, a really strong clustering performance quantitatively. So again, just reinforcing there is this natural clustering of this database based on the H11 value correlated with these weights. So that concluded our unsupervised analysis where we use PCA and clustering. So now to go on to some supervised work, perhaps the most obvious thing to do is, since we have these 5 vectors of weights and we have these Hodge numbers about the hypersurfaces within these projective spaces, we do the problems of learning each of these parameters from the 5 vector of weights, where obviously the Euler number is just some simple linear combination of these weights, the difference between them doubled. So the structure we use, because there's quite a range of integer values the numbers can take, we construct this as a regression problem where we used sort of the most simple structure, the ReLU neural network with 3 layers of these neurons, the most standard mean squared error loss, an Adam optimizer. And then again, we do 5-fold cross validation without. So we take 5 partitions of the data sets and train 5 independent nets on each of those. So we get a sort of a 5 different measures of the performance we can average and take standard error for. So the measure we use to assess performance is this R-squared measure. For those who may be less familiar, I'll just quickly review it. And the idea is that the R-squared measure compares the performance of predictions of the nets to the performance of some null model that always predicts the mean of the output that we're looking for. So you can see in the scenario where it's predicting worse than the mean, the numerator will be very large. We have R-squared less than 0. Where the net is predicting just as well as the mean each time, these are going to equate and we're going to get an R-squared value of 0. And where it's predicting much better than the mean, in fact, in the case of perfect prediction, where all these numerators is 0, we're going to have an R-squared value of 1. So we can see for each of these supervised problems, we're going to get R-squared values very close to 1. So again, sort of this is a very nice result to see. We're getting very strong learning of these topological parameters of the hypersurface from just the weights of the ambient projective space among them. So perhaps that could be something that's unexpected, but I should also add that there are known formulas that already exist to calculate Euler number and Hodge numbers from the weights. Again, from these excellent papers from earlier on. But I should add that these are particularly non-trivial formulas. So you can see here, I've given the formula for Euler number from the weights, and the formula for Hodge numbers is even more complicated based on the Poincare polynomial and other factors to calculate. But I should add, we obviously have a sum of a lot of products. And in particular here, we have divisibility checks, which are happening tens of times throughout the computation of a single Euler number. And these involve greatest common denominator computations, obviously something which neural networks perform notoriously badly at. So the fact it can learn anything despite having to rely on, if it was having to learn this formula, it would have to learn to compute tens of these checks, which it would usually perform badly at. So again, it's reassuring that it's managed to learn and approximately to such a good level. And again, perhaps this could be related to this clustering behavior from H11 to the weights, as we discussed previously with the unsupervised methods. So that was a regression analysis, supervised analysis. So as well, because we had 4 databases, we thought it appropriate to do some binary classification as well. So here it's simply a balanced database of a sample of the weights that give Calabi-Yau hypersurfaces, and also weights from the other databases that we call non-Calabi-Yau. And we do that for each of these cases of non-Calabi-Yau being in each of these. And the architecture, the classifier architecture, is then learning whether it can distinguish some given 5-vector. Can it see whether this represents some weighted projective space with which can admit a Calabi-Yau hypersurface? So definitely something quite non-trivial that it can try and learn straight away. So the architectures we use, again, we use the same ReLU neural network architecture we had from before, but obviously this time now it's a classifier. We use a cross entropy loss over mean squared error. And as well as that, we use, probably the most simple binary classifier architecture. We use the logistic regressor. So here in particular, there's only 5 weights or 5 hyperparameters in this that need to be trained for the prediction. And on top of that, we also use a support vector machine, and obviously another standard binary classifier method. So for these results in each of these cases, these are the accuracies for the test data. And in each case, we can see we're getting pretty good performance. Performance accuracy is always above 70, so quite good. It's certainly learning some kind of behavior to be able to predict this Calabi-Yau-ness, whether it can be Calabi-Yau can be drawn within the space. And particularly the neural networks perform better for these random and co-prime databases, over 90%, so a more reassuring result for machine learners. But interesting enough, when this transversity property is included into the database, the non-CY database, such that all of the trained database trained and tested on has transversity, then the performance drops. So again, this is probably indicating the net is somehow using this transversity in these 2 cases to do the prediction. And interesting enough, when at this transversity level, we see that this really simple logistic regressor architecture is performing just as well as the more complicated neural network architecture. So it's really very impressive that such a simple structure can do such a good job in determining or distinguishing whether there's a hypersurface or not. But as I said before, 75%, these are good results, but these aren't the things we aim for as machine learners. We want over 90s, over 95s. So we wanted to, delve a little deeper into what was happening here. And for this, we do some misclassification analysis. So in each case, we take a logistic regressor and we take just 50 Calabi-Yaus and 50 non-Calabi-Yaus from each database, so a small database, train it on that. And then we run all of the Calabi-Yau data through it so that it's, so that it can predict whether each of the Calabi-Yau data is correctly classified to have a Calabi-Yau hypersurface, which we plot in orange, or incorrectly, which we plot in blue. And here we can see if we pre-train with the random data, if we plot this misclassification on the standard Hodge plot, then very interestingly enough, there seems to be some bound above which above some bound for H21 around 100, where there is perfect classification. So if the Calabi-Yau has some specific extreme of this H21, then a simple pre-training with random on this very simple architecture can perfectly predict whether there's going to be a hypersurface or not. And conversely, and again, perhaps unexpectedly, if we instead pre-train with the transverse data, now we have similar behavior at the extremes of a Hodge number, we have perfect prediction. But in this case, it's now some bound based on H11, where there's perfect prediction above this bound. So these sort of plots are sort of supposed to exemplify that. It looks like the prediction of Calabi-Yau-ness from some set of weights seems to be coming from some correlation to the Hodge numbers. So if we wanted to probe this a little bit further, and for this we do some partitioning on the data. So we split the Calabi-Yau database, this 555 size, up into 50 bins, and we optimize these bin bounds such that there's roughly the same number of 5 vectors in each bin, these sort of roughly 100 to 200 each time. And then within each bin, we then sample either, in this case, we use random. We're partitioning the data according to its H21 value. And then we have sort of 100 Calabi-Yau 5 vectors per bin, and we add another equal amount of non-Calabi-Yaus. And in this experiment, we used the random for the non-Calabi-Yau sampling, because we saw that for the random pre-training, we seem to have some bound based on H21. And in this scenario, for the H11 partitioning, we use transverse as the non-Calabi-Yau data to sample for each bin, because again, we were H11 partitioning, we saw some bound here. Oh, thanks. So then performing the logistic regressor training and testing on the data within each bin, we then plot the accuracies going across, and you can see as we expect from that previous plots, at lower values of H21, we have a lower performance of accuracy, but still not dropping too low. But as we get to the extremes of H21, we get up to perfect prediction from this very simple architecture to be able to predict this Calabi property. And again, then for the H11, pre-training with the transverse data instead, again, we have this similar behavior, but now at low H11, we again have this drop off in performance, which then increases to perfect performance again at this extreme of Hodge number. So on top of these accuracies we plotted for all the bins, we also plot the logistic regressor hyperparameters. So it's a simple architecture, there was only 5. And we can see that where we get to these high extremes of the partition, where there are perfect prediction performance, then it looks that only 2 weights are really separating out in their absolute values. And these bounds represent averages, but there's really just two weights become dominant in being able to determine whether there is a Calabi nature or not. So it doesn't even need to use all 5 weights to do this determination. And whereas here we have the first and second hyperparameters become the most dominant, when we pre-train with transverse and predict the other way around, then it becomes the second which becomes the most dominant and the first less dominant, but still the same 2 that are the most important. So we sort of again have sort of a converse behavior where the 2 dominant weights are swapping their dominance, and these working at different extremes of the Hodge numbers for this prediction. So that sort of covered everything we discussed in the paper and we looked at. So to summarize briefly, we did some unsupervised methods, particularly linear PCA and then some clustering. And we saw that this Calabi database naturally sorts itself into classes based on the H11 values of the hypersurfaces within them, which we confirmed with a good inertia score from k-means. And we again say we corroborated with this similar structure from PCA. And then beyond that, we then did some supervised ML, and we saw that sort of a simple network architecture can learn well with each Hodge numbers, despite very complicated formulas from them. So perhaps it is making use of this linear relationship to learn some approximate relation. And then beyond that, these Calabi weights can be very well distinguished from non-Calabi weights with simple architectures. And in fact, we can get up to perfect prediction distinguishing if we look at particular extremes of the Hodge numbers. So that's everything I wanted to talk about today. Thanks everyone for listening. And of course, I'd love to have a go answering questions if anyone has any.
Thanks very much. Questions for Ed?
Thanks.